All right, so 3.2, folks, it's going to talk about least squares regression. We're going to talk about what least squares is, but first, let's do a little recap, a review from Math 1. So today we're going to talk about regression lines. So this whole first part of this last unit in stats is going to be talking about transitioning from one variable to two variables. We're going to talk about bivariate data. Bivariate means two variables. That's going to be different from the univariate data that we talked about previously to this. Right, Miranda? Shh. Okay. Now I had to shush her on YouTube. You've been shushed on YouTube, Miranda. Okay, so a regression line here is used to predict y values given x values. All right. So the big idea is we're actually predicting values, all right, for y given an x. Back in Math 1, you called these independent versus dependent variables. You also talked about y depending on x. All right, so x is what's going to increase and not be dependent on the y value. So the y value is going to be dependent on whatever that x value that you put into it. So we're going to use a regression line to talk about this. So literally, we're going back to lines. Most times, we're going to be talking about how to do this via your calculator. Either they're going to give you a picture of a scatter plot with the line, they're going to give you a table where you have to come up with the line, or you might have to use your graphing calculator in order to calculate the line, which is what we're going to do today. All right, so here's a picture of a regression line on a scatter plot. So for the homework over the weekend, you talk about scatter plots, you talk about ways to describe scatter plots. Today we're going to be adding like a numerical summary with it, but the numerical summary is actually like a prediction model. And that thing is called the regression line. So this example is on in your book on page 164. It's talking about the relationship between fidgeting and fat gain. All right. So have you ever I guess fidgeted when you're taking a test? Do you guys know those people who are with their legs? They're just you know what I'm talking about? Yeah, that's called fidgeting, which is fine. But what they're saying here is that there is an association between your fidgeting and your fat gain. So what can you tell me from this scatter plot happens? So the more you fidget, what? The more calories you burn by fidgeting, the lower fat gain you're going to have. So it's going to decrease your fat gain as the calories that are burned by fidgeting increase. Does that make sense? Okay. So what this red line is doing, so this is how you interpret the least squares regression line. This goes in the blanks there. It's a prediction line based off the scatter plot. It uses every point. So it uses this point up here, or it uses this point down there. Actually, it uses every single one of these data points. And what it does is it says, okay, we're going to try to get all of these data points. And it says, all right, we're going to find the line that gets through as many points as possible. Right? And that's why you call it the line of best fit. This should be a lot of review from Math 1. This is where you learn it. This is back in middle school. Maybe in 9th grade. Okay. But this is early on in your high school career. Most of you guys are juniors and seniors. So this is like a throwback to the past. All right? But anyways, what this regression line does is it accounts for every data point on a scatter plot, and it tries to provide the best line that fits each of those values. Is a regression line perfect? Sometimes. Is this one perfect? No, because some values on the scatter plot lie above the prediction line and some lie below. All right, and we're going to talk about the errors within a regression line, and we're going to talk about different statistics to kind of calculate those error or that error. Okay. First thing here is what the form of a regression line looks like. So in statistics, we usually say it's y hat equals a plus bx. Now this is not like the line of best fit that you see from Math 1. In Math 1, you see y equals mx plus b, right? Slope intercept form. What's the first thing here that you see from Math 1 linear regression to AP Stat linear regression? You see y hat. Why do you guys think we put a hat over it? It's like a sample, because remember that your data comes from a sample, so it's like a sample y. We call it a predicted y. So this is going to be when your values are going to be predicted by your scatter plot or your least squares regression line. All right, so we have a y hat. Notice here if we interchange the y-intercept, which is b, with the slope times x, it's kind of looking like this. Do you guys see how it's almost in the form? Yeah. However, in stats, what else do we do? We change b to be a, and we change m to be b. So we actually write it like this. But it's pretty much the same thing, right? Okay, so we need to figure out what's what. All right, so this y hat, as you've already picked up, all right, so I'm going to erase this real fast. That y hat, as you already picked up, is going to be the predicted y value. All right, so basically, it's going to be a guess at what the response variable value will take given a specific x value. So if x is 10, what's the predicted y value? If x is -5, what's the predicted y value? All right, that's what y hat's going to be. It's not going to be the actual y value of the data point. It's going to be what you predict it to be. Two other things here that we're going to talk about is the slope and the y-intercept. You're going to need to know how to interpret these very, very, very well. Last year on the AP exam 2018, I graded question number 1. Question number 1, part A. Interpret the y-intercept in context of the scenario. So you're going to need to know how to interpret the y-intercept. All right, and we're going to talk about that today. First, B is the slope. What that represents is it's the change in the predicted y value for each additional x. So it's the change in y for every increase in x. But we're going to change that definition to be the predicted change, all right, because it's based off a model. It's not how it's actually changing, it's how we predict it to change as x goes up. Does that make sense? Mm-hmm. Notice for the y-intercept, this is the predicted y value when x equals 0. So when your x takes a value of 0, what's the predicted y value? Sometimes it's going to be hilarious because that y value doesn't make sense in the context of that scenario. For instance, if you have a negative y-intercept and you're talking about the number of hours of sleep, like sometimes it does not make sense. So like maybe you get a negative GPA because you didn't sleep at all. Well, yeah, your probably GPA is going to be a lot worse, but is it going to go with a negative? No, but sometimes your regression line will tell you that because it's just that. It's a prediction. It's not what's actually happening, all right? So you need to make sure you're accounting for that. All right, before we get started, we need to make sure that your diagnostics are on in order to find the correlation. You talked about the correlation within the video this past weekend. Make sure that your diagnostics are on. You can do that a couple ways. Make sure you write down these steps. These work regardless of your calculator type. If you do second, 0, and then you want to look at the catalog menu, you go down to the D's for diagnostic on. Make sure you press enter twice once you do that, and then it will give you a message called done. If you have one of the newer calculators, I'm going to show you how to do it. All right. So if you have one of the newer calculators, I'm going to show you how to do it. So going over to the TI, if you guys hit mode, you guys see how I hit mode here? It brings up this menu. Notice that if you go down here to stat diagnostics on, you guys see that right there? You need to make sure that turns on. All right? And then that will make sure that you get all of those values. All right? Does that make sense? Mm-hmm. All right, so a couple ways you can do it. I'll let you guys take a second just to write those down. And then we are going to get started with an example. Does anyone have any questions about how to turn their diagnostics on before we get started? Yes? No? Maybe so? Did you find it with your calculator? Because you need to actually literally turn them on for the example. Okay. Are we good? Zach, question?
Is this one of those things that, like, if you just leave it on, it won't have, like, any effect?
It will have no effect other than giving you extra information. Okay. Yep. It's not like if you convert your calculator to degrees and radians and messing up your trig stuff. Okay. All right, so our example here is going to be about used Hondas. I know you guys are excited about that. Anybody have a used Honda? Do you have a used Honda CRV?
No.
Okay, well that's what we're talking about. Okay, so the following scatter plot shows the number of miles driven and the advertised price for 11 used Honda CRVs from the years 2002 to 2006 models. Now, what we're going to do is, you guys have this on your paper. It's not up here on the board, but I already have a scatter plot here to show you. But you guys see you have a table of values over to the right on your notes? Okay, we're going to use those, and we're going to type those in, and we're going to come up with this regression line, and we're going to write it here. All right, you guys good with that? Okay, so go into your calculator. You're in what class? Stats, right? Oh, I'm going to go turn my diagnostics on. And then I'm going to second quit, and I'm going to go to stat, and then we're going to go to edit. All right. You want your explanatory variables to go into L1, so you guys should know where to find L1, L2 very quickly, because we use that for other stuff. And the response variables should go in for L2. All right, so I'm going to type as you type. So no talking while you're typing in stuff. As soon as you start talking, you're going to type in something wrong, and then you're going to raise your hand. Mr. Bird, I haven't typed in something wrong. And I'm like, Madison, because you were talking. Oh, you don't want to type it in? Someone else doesn't like to type in values, too. All right. You guys good with that? Make sure you double check your values. Make sure you. I sometimes need to do that. Okay. I think we're good. Am I good? Yeah, we're just right. You guys will make fun of me if I'm wrong. So, okay. We're gonna go to stats. Anybody remember how to do a linear regression? You think we should? We're going to go over the calc. Now, 4 is the premier option back from Math 1. However, I want you to think about the form of the least squares regression line that you wrote on your table.
A plus bx.
A plus bx, right? You guys see that's number 8?
Yeah.
All right, so I want you to hit 8. You guys see L1, L2 there? Make sure your x's are list 1 for your explanatory, y list 2 for your response. And then we're going to go all the way down to calculate, and boom, least squares regression line. So stat calc 8, and then you should get all this. Now, if you have your stat diagnostics on, you're going to get r squared and r. Today we're going to talk about r again because we should know that as the correlation coefficient. You guys remember knowing that as the correlation from video from Sunday? Hopefully. Correlation is the number between -1 and +1. With 1 meaning it's stronger, 0 meaning it's weaker. You guys should know that, right? Okay. R squared we're going to talk about tomorrow. That's called the coefficient of determination. All right. And we're going to talk about what the coefficient of determination tells us about our least squares regression line tomorrow. However, what's our task right now? Write the regression line. Do you guys see that's going to be the 18,773.28 and the -86.18? All right, now, a lot of you guys are probably going to write y equals, but I don't want you to write y equals. I want you to write cost with a hat. You see how I wrote cost with a hat? Cost is wearing its little party hat. Oh, that's terrible. Let's do that again. This is harder than it looks. All right, very good. Sound effects always make it easier to draw. So that's going to be equal to 18,773.28 minus 86.18 times. Now, notice that I used the context of the scenario for talking about the predicted value. What should I use over here? So cost was my y value. What is this? Number of miles driven over there. This way you don't have to deal with x and y, because if you literally write x equals and you write y equals, you have to define them. So you would have to come over here and say y is equal to the cost. You need to say x is equal to the number of miles driven. Does that make sense? Like if you use x, y, you have to define what they mean. What is x equal? What is y equal? Guess how you can avoid that? Doing this. When we do some of the free responses for the AP exam, you're going to see that a lot of the scoring guidelines do this, which is why we're going to do that. All right, does that make sense? Good? All right, so for part B and part C on your paper, you have interpret the slope, interpret the y-intercept. All right, you guys ready to do that? Okay, slope. How do I interpret the slope here? Go back to your chart. What's the generic idea?
Every 1,000 miles driven.
Well, you're talking about it in context, which is good. But just generically, for every increase in x, what's changing? The predicted y value. Remember, because it's from a regression line. It's a predicted y value. Right, so let's do that. So the slope here you can identify as negative 86.18. So in context, for each additional 1,000 miles driven, the predicted price of the car is going to decrease by $86.18. So here, or you can word it like this, as long as it has that general idea. So the predicted price for a 2002-2006 Honda CR-V goes down. Why is it going down? It's going down because it is negative, correct? For each additional 1,000 miles driven, and notice that's for each additional x. That's for each additional x item. So you guys need to know how to do that in and out. So to interpret slope for each additional x, it's the predicted change in y. In this case, for each additional 1,000 miles driven, the predicted price of the car decreases by $86.18. That's good? You understand how to do that? All right, so tell me, generally, how do you talk about interpreting the y-intercept? What's the generic idea? It's the starting value. So when x equals what? 0. It's the price of the car, the predicted price, correct? So what does 0 represent in this case for x? If there are 0 miles driven on a used Honda CR-V, wait a second. 0 miles driven on a used Honda CR-V. Well, it doesn't always work, right? But can the predicted price be $18,773? Is that a valid price for a car? The answer is yes. That's actually okay. All right. But anyways, it's the predicted value or the predicted price of a used Honda 2002-2006 CR-V with 0 miles driven. Now that doesn't make a lot of sense because it won't be a used car if there's 0 miles driven, right? But again, regression lines do this. Do regression lines know what they're predicting? No, they're not sentient beings. However, guess who is? Most of you. Most. Okay. So use your, awareness to be like, wait a second. Something's awry. Awry means off. Use that on the AP exam more.
What is that other word you said? Sentient?
Sentient, like you have awareness, you're cognizant, you're a person. You're alive. Well, some of you, which is why it was a joke. That's why it was a joke. I mean, most of you. I got a little chuckle, but not like a super laugh. It was kind of like one of those in the middle jokes, probably like a 4.5 out of 10 kind of thing.
It's a YouTube thing.
Take that somewhere.
Maddie, put your phone away.
Okay.
Now I had to scold you again on YouTube. Well, that was Miranda earlier.
Yeah.
Now you're scolded. Teaching high school, folks. This is what I do. All right. Anywho, describe the correlation. So the correlation. Can anyone tell me what the value of the correlation is? You found it. It's probably on your calculator if you didn't press clear.
Oh, it's -1.87.
So it's R equals negative 0.874. You guys remember how we described the correlation? We called it the new socks. DOS. Okay, can anyone share with the class and our esteemed guests in the room what DOS actually means? Direction, outlier, form, and strength. Whoa, I don't know that word. But strength is what that word is. Okay, so here you go. Direction. How do we describe direction? Negative or positive? This is obviously negative because it has a negative sign. Okay, so negative, that's the word we're going to use. Okay, does it look like it has an outlier? If it doesn't have an outlier, should we mention outliers? No. Moving on, form. What form are we looking at here?
Linear.
Is it pretty linear or is it curved?
It's approximately linear.
It's approximately linear. Good. Just in case we're unsure, it's approximately linear, right? And then what about the strength? Would you call it pretty strong, pretty weak? Because you can actually use this numeric value to tell. It's pretty strong. So we would say there is a negative
Approximately linear.
and strong what? Association. That's the key word there, Calvin. Association between the number of miles driven and the cost of a used Honda CRV, right? Something like that. So here is a nice typed up, pre-read, pre-assessed, making sure that my students have the best education possible response that's easy to write down and understand. You're welcome ago. Welcome from like 5 years ago meetings. This is me 5 years ago. Are you thinking the past me?
Yeah.
You're welcome. Well, from past me. Past me says you're welcome. It knew 5 years down in the future that Courtney Keeler would be sitting in here and being very appreciative of work of 5 years ago. I think I actually was, this was the year I made it when your brother was in class. Aaron, yeah. It's 5 years ago. It's 2014. It's great. Back in the day.
Like a TV show, watch that, where it just like goes back and you're like, thank you.
Well, that's a thing. All right. How do you guys think you pronounce this word?
Extrapolation.
Good. It's not extrapolation. It's extrapolation. Good. Just want to make sure we know how to pronounce the word before we use it. Okay. Now, extrapolation is this. Does anyone know what it means to? Here, I'll erase that. Does anyone know what it means to extrapolate before we talk about it? Yes.
Like, usually it's like down data on stats, and it's like taking data from some.
It's okay. Keep on.
Yeah, it's basically just taking data from like a huge amount of information, and yeah, I feel like it's very vague.
All I can hear
Like,
now is your voice and extra.
Is it like when you make a prediction?
Zeke, you're a little bit closer. So it's making a prediction without knowing something or doing something.
I was just gonna say it's like deriving information from, you know.
It is, but it's doing it not great. So extrapolation in stats is when you create a least squares regression line and you use it to predict values outside of the range of values used to create the line. So for instance, in our little scenario, we used miles from 22,000 to 86,000 miles, correct? If we wanted to use this to predict for 200,000 miles, that would not be a good result because 200,000 miles was not used in the creation of our least squares regression line. Therefore, we're extrapolating. We're taking a guess based off a model we have that didn't include that value. If that makes sense. So extrapolation is going outside the range. It's basically being extra. It's being extra. Okay. So what we're going to do here is we're going to, can you use it to estimate this value? So I have a question. Can we use it to estimate 50,000 miles? Is it safe to say, what's the predicted price of a Honda CRV that's used with 50,000 miles? Yes, because notice that 50,000 miles is in between the minimum value of 22,000 miles and the maximum of 86,000 miles driven. Can you quickly do that? Yeah, okay, so there's 50,000, go over there. So it's going to be roughly there. Can we do better than that? What can we do? Good, you can type it in to the equation. That's what I mean, you guys can just, stare at it all day. I'm going to plug it into the least squares compression. That's what I'll do. So I'm going to say 18,773 minus 86.18, and I'm going to times that by 50, because that's the number of miles driven in terms of thousands. Okay. So if you know you need to do that, guess what you can do now? You can take your handy-dandy calculators and you can type in the numbers and see what number you're going to get from this, right? I can play the Jeopardy music for you if you want. Do 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 do. All right, are we done yet?
Yeah.
Okay. What's the predicted price of a used Honda CR-V with 50,000 miles? So about 14 grand, 14.4 grand, something like that. Cool? Okay. So you guys are okay with us using our model to predict this kind of value? This is not extrapolation. Why is this not extrapolation? Because 50,000 miles was used to make the regression model. Okay? Should we predict the asking price when we have 250,000 miles? Yes? No? No! No, you shouldn't. Why no?
It's outside of our range.
Because predicting within the range of xi's allows for less error. So we should definitely keep to values that are close to the range of 22,000 to 86,000. Now, my opinion is, if you can extrapolate a little, it's not going to hurt. However, beware. Technically, it is extrapolation if you go outside of 86,000. But if you go to 90,000, I think it's pretty much the same. What do you guys think? What about 20,000? That's kind of close to 20,000. A little bit of extrapolation. What about 250,000? That's supremo extrapolation of. That's a no-no. Don't do that. Okay. All right, so what are we taking away from extrapolation? Number one, how to pronounce it. Number two, what else? Don't, it's not a good thing, right? Extrapolating, not very good, right? 3. If you go outside the data range to use to predict the values, probably not good. Okay, don't. All right, residuals. Anyone know mathematically what a residual is? That's what second period told me, what's left over. Okay. A residual is the difference between the observed value and the predicted value. Or it's just observed y minus predicted y. Or it's just y minus y hat. All right, so here's a picture that's on your notes, correct? Do you guys see these vertical deviations here? These are the illustrations of residuals. Basically, it's the difference between the observed and the expected counts. Notice I use the word expected instead of predicted. Why do you think I use expected? What does observed minus expected sound like?
Oh,
It kind of sounds like pi square, right? So that's a similarity between some of these. All right. However, do you guys notice the distance here compared to, I don't know, let's say this distance here? What's the difference there? One's bigger and one is? Smaller. So I have a question. Are residuals wanting to be small or big? Do you want small residuals or big residuals? Small, because if you're talking about the difference between them, you're talking about basically what? You're talking about the error. It's how far you're off. Right? How far you're off. Do you want to be off when you're predicting? No, you don't. You want to be as close as possible. Like, for instance, this past weekend when people are betting on the Kentucky Derby, do you think those odds makers want to be off in their models? No, they want them to be right on. So if they have a lot of error, not a good thing. So we want small residuals. Okay?
Who just asked us how a horse is?
That is a horse race, yes. Okay. Now, notice that positive residuals are above the line, whereas negative residuals are below the line. Okay? However, it doesn't matter if they're positive or negative. It doesn't make it any more, I guess, in error. Like, negative residuals are not more erroneous. Is that a word? Yeah. Is a word? Okay. I think that's a word. Are not more erroneous than positive residuals. And vice versa. Just because a residual is positive doesn't mean it has more error than a negative. All right? Error is error, my friends. Okay. You guys good with this? So what is the takeaway from residual?
Above one is positive, below one is negative.
Okay, and it's basically, oh, I erased it. It's error. It's basically how far you're off in predicting. Okay, so what we're going to do here is we're going to predict it for this point here. Okay, what is the residual for this point? Do you guys agree that this has a residual?
Yeah.
And how do you know something has a residual? If it's not it, what is it? If the point is not on the least squares regression line, it has error. I have a question. It's a vertical distance, correct? So will this have a positive or negative residual? Go find it. Go find it. It's like go fish. Go find it. Right? Do you guys understand that this is the observed value? So how do you find the predicted value? Plug it. What's it? Nope, not the predicted value. Plug the 70 into the regression line. Okay, so you need to plug in 70 regression line. All right, take a minute or two or 17, preferably not 17, but take a couple minutes to do that. All right, so let's go over this one. So you should have used your equation to predict the value for 70,000 miles driven. So you should have plugged in 70 there. Anybody want to say what they get? 127.
12,740.40.
I got this. That's tough.
Yeah.
How far are you off? So you're off 28 cents. I'll spot you the 28 cents.
Okay.
All right, so my question is, how do you find the residual? Plug the X value into the thing. We do not need to plug in the X value to the thing. We just need to do the residual, which is the observed minus the predicted, correct?
That's what I meant.
So those are not X values. I have no idea. But anyways, you're supposed to take the observed and subtract the predicted or expected. And what do you get?
1,709.6.
Or point whatever I got. So you might be off a little bit. I don't think I actually used the 0.28 here. So, oops. It's close enough, right?
Yeah, both, all of us have that answer.
You know what? I could do 15,000 things right, but you're going to make fun of the one thing I do wrong.
No, congratulations, I think you did right. And then the point.
What did I do right here? Because you've already pointed out my flaw.
You read residual correctly?
Yay, me! Yes! All right, what else I do?
You wrote the equations out? Your teacher as well?
Where's my hand clap? I don't get a clap? I got a stated elevation of that. I'm just joking. I'm just joking. Oh, that's a little bit. All right. Now, a couple things here. And I'm going to show you the graph in just a second. If this residual happens to be positive, that means you have underpredicted the y value. And we're going to talk about that. I mean, it doesn't make intuitive sense, but once I show you, it's going to make a lot of sense. It means you underpredicted. If the residual is negative, that means you overpredicted the y value. All right, I'm going to go back to the graph over here. Not there. This one. Okay. Okay, so here is the predicted value, right? No, I lied. That's not the predicted value. This is the observed value. This right here is the predicted value. Do you guys see that this is positive? Okay. Which one's bigger, the observed or the predicted? The observed, which means you did not predict enough. If your prediction is there, it's lower than the observed, which means you under predicted. Does that make sense? Vice versa. Here, this is the observed value. This is the predicted value. If that is going to be a negative residual, that means you over predicted, right? Your prediction is too much. It's over the observed value, all right? So that's what this thing, hold on, here says, these two things. So I have a question. What did we do here? If we have a positive residual, did we under or over predict? So we are going to say here that our least squares regression line under predicts the cost of a 2002 to 2006 Honda CR-V based off the number of miles driven by roughly $1,700. Okay? So our model under predicted. It's kind of like this. It's kind of like when you get a bill and you're like, oh, that bill usually averages $100. And then all of a sudden, it's $107. You're like, what the crap? Right? No one? Is that just me because I pay bills? Yeah. Okay. This is why your parents yell at you to like not turn on the air conditioning until like July. Because it reduces bills, right? So they have a prediction in mind of what it is, and if it's under that, no one cares. It's like, oh, cool, nice. Under predicted. My power bill is less. Excellent. However, it's over predicted. Right? So here, would you be okay with an under prediction of cost? You're going to a car lot. You're thinking it's going to cost you $16,000 to get a car. It only costs $14,300. Are you happier?
Yes.
Yeah, in this scenario. So putting yourself in the scenario kind of helps if it's like a nice benefit. Like, oh, cool, it's less than I thought. Wrap it up, put a bow on it. Can I get some serious radio? Because I have this extra $1,700 now. Can I get some cool rims on there? Yes, ma'am.
So how can you say that it predicts the cost for the whole regression line?
It doesn't for a whole thing. It just does for that specific point.
But like, in the thing that we wrote, we said for 2012. Okay.
Oh, it's just for this number of miles driven. It should be, well, we should probably specify. Probably something about 70,000 miles driven, if that makes sense. We should probably narrow that down. You didn't say what our question was? No. This statement kind of referred to like the whole thing instead of just for that number of miles driven. It should be specific and probably for 7,000. All right. Now, why do we call this thing a least squares regression line? I've called it a regression line. I've called it a prediction line. I've called it a line of best fit. I've called it a trend line. But why do I keep using the words least squares regression line? Very good, Madison. You can read. I'm so proud. Okay. Basically, when we talk about that error, the residual, it's a vertical deviation, sometimes positive, sometimes negative. Remember, sometimes with the standard deviation and sometimes with our chi-squared statistics, if we add up all the errors, what do we usually get? 0. So what do we end up having to do? Square it, right? So this is what it visually looks like. Do you guys see that this square has area this square here has area, that square here has area. Do you guys see how all those have area? What the least squares regression line does is it makes sure that there is one line that makes the sum of all those little areas the smallest. And if the sum of all those areas is the smallest, it's the best prediction line. AKA, it's the least squares regression line. All right? So there's only one line that makes it the best. So a line of best fit, a trend line, a prediction line, back from Math 1, is technically a least squares regression line due to this idea of minimizing the area of the squared residual. Does that make sense? So the reason we call it a least squares regression line is we're trying to min that area. Because if we min that area, we're minimizing the error within our prediction values, thus coming up with the least squares regression. A least squares regression line is the best linear model we have for a set of data if it follows a linear trend.
So if they're the same, why don't we learn that in Math 2?
Because your brains can't handle it there. You get smarter as you get older.
Math 1 was making
Just not so sure about that, Mr. Burton.
sense.
Okay. No, I think it's because you're trying to lay in all the basics. So you've already had a foundation once for Math 1. I think here we can get a little bit more nuance. There's a little bit more to it. If we try to like give it to you all at once, it's like, whoa, overwhelming. It's like a tsunami.
Like in history, you learn the same thing every single year.
Kind of. Hopefully that one year it kicks in, right? But no, it's like foundational. It should be. It's kind of like how you learn how to factor in all of your math classes. By hopes that you get to pre-calculus, you actually know how to factor. Okay. Or maybe you don't. No, that's okay. All right. Okay, last thing for today, and then I'm going to give you time to work on your AP multiple choice assignment, is you can actually calculate a least squares regression line from using the average of the x values and the y values along with their standard deviations. Okay. So let's go back to your little chart here. Do you guys see the chart on the front page here of your notes? The x values and the y values. Do you guys see those?
Yeah.
Okay. X bar is when you literally add up all the x's and divide by 11. The y's are when you add up all the y's and you divide by 11. That's what x bar and y bar are. They're from the table, finding the average of x and the average of y. Okay? I'm going to calculate this for you so you can see. Generally, we use our handy-dandy calculator to do this. Do you guys remember going to 1var stats? If I have list 1 here, what am I finding the stats of? The x values, because x values are in list 1, right? Do you guys see that this averages to 50.5? So of the 11 cars, they average 50,500 miles driven. What's the standard deviation of that? 19.26, right? So this right here is the x bar. This is the s sub x that we're referring to. Does that make sense? Okay. When I do my 1var stats, I can change the list, right? So I'm going to stat, calc, 1var stats, second 2. Do you guys remember changing the list there? And this is going to be the average for the y's. Do you guys see how your average y is going to be $14,425? That means the average price of one of these 11 Honda CRVs from the years 2002-2006 is $14,425. Yes with me? What does that vary by? About $1,900, roughly $1,900. Do you guys see that? Okay, that's what those are talking about. Now, if you know all of those values, you know the y bar, you know the x bar, you know s of x, you know s of y. What I'm telling you here is you can actually come up with the least squares regression line using these two formulas. Okay? For the sake of the class, we're not going to prove how these formulas work. We're just going to apply them. These are found on the formula sheet, but you actually have to write them in because I did not print that part. Oops. But write these in the little section in your notes. Do you guys see how you can come up with the slope? To find the slope, you can take the correlation, times it by the standard deviation of y over the standard deviation of x. For y-intercept, you're going to say a is equal to y bar minus b times x bar. And we're going to do an example. We should already know what our least squares regression line is for the Honda CRVs. We know that's 18,773.28 minus 86.18 times number of miles driven. We're going to see how we're actually going to get the same thing roughly by using these two formulas. All right, you guys ready for it? Okay. So notice here that I already gave you this information in the problem, right? Do you guys remember that we came up with the 50.5, the 19.3, the 14,425, and the 1899? Those are the standard deviation and the means for x and y respectively. All right. So can we find the equation of the least squares regression line? Answer is yes, Mr. Bird, we can. How do we do that? Cool. Well, you do slope first. Slope is equal to r times s of y over s of x. So you take correlation and you divide it by the ratio of the standard deviations, y over x. Makes sense. Notice that it's y over x. Y over x. Isn't slope the change in y over the change in x? So you put the y on top and the x on the bottom, change in y, change in x. This is the average error for y, average error for x times correlation. All right, I'm just saying words now apparently. So correlation's negative this. Negative 0.874 times standard deviation, which is 1899 over 19.3. Is that right? Behold the magic of statistics. You can't see my answer. Someone tell me what that is.
-86.
Did you calculate it, or did you watch me write it?
Just write it on your shirt.
It's not on my shirt. Okay, maybe it's. It's -86. Did anyone confirm that?
Yeah.
Negative 85.99 something.
Yeah.
Isn't that fancy? Good. How do you find the y-intercept? A equals y bar minus b times x bar. All right, what's y bar?
No, sorry, 14.
That's 14,425 minus a negative 86. Let me give myself some more room here. Crap, I did. Okay. What's the mean there? 50.5? I give you a hint. The first two digits are going to be 1,8, just like the y-intercept for the regression line we already done. So 17 or 18.7 what? 68. That's pretty close. So it seems like we're off by about $5. Doesn't that roughly the same regression line? So guess what you can do? You can put the pieces together. So I guess it'd be y hat is equal to 18,768 minus 86x. Just make sure that you do what if you're going to use x and y? Define them, right? Here we're defining x to be the. It's the same regression line, guys. It's literally the same one. Like the 18. Instead of 773, it's 768 minus 86x. X being the number of miles driven in thousands. The other one being cost, predicted cost, right? All right. So right here, can you explain what the change in price would we expect for each additional 19.3 thousand miles? This should be additional. Sorry for the error there. What does it sound like I'm talking about? Which value? If I want to say, what's the change in price for each additional 19.3 thousand miles? Well, this additional 19.3 thousand miles sounds like what? Oh, I didn't even notice I forgot standard deviation. Ooh. PowerPoint, rough. Right? So doesn't that sound like, this sounds like S of X, right? Which one dealt with S of X? B or A? Slope or the y-intercept? B. Well, B was the R times what? S of y over what? Which was equal to what? That's negative 0.874 times 1899. And isn't that technically all divided by 19.3?
Yeah.
You guys see that? That's technically all divided by that. So think of this as like the per 19,300 miles. So if that's the per 19,300 miles, that means what would this be? What's the product of this?
The decrease.
That was going to be the, that's the change in price we would expect. Well, as you drive cars, do they gain or lose value? So we expect the price to go what? Down. That's why here, when you take the product of those two numbers, that's going to be what you expect it to decrease by. What's the correlation? Negative 0.874 times 1899. What is the product of those two numbers?
Negative 1659.77.
So negative 1659.77. So roughly this. Negative 1659.73, something like that. So guess what that means? That means we would expect the price of the car to decrease by that much money for each additional 19.3 thousand miles driven. Okay. So the key there was to kind of interpret that this 19.3 thousand miles connected to this standard deviation, which is S sub x. Right? So multiplying the correlation times that numerator of S sub y would give you that. All right, and that will be the end of day one, folks, for least squares regression lines. Tomorrow what we're going to do is talk about residual plots, talk about R squared S, and we're going to bring it together with talking about how to interpret mini-tab outputs and JMP outputs for least squares regression, which is pretty easy, actually. So you guys will like that. Today is a lot of the grunt work. You guys good? Questions? Nah? Yes? Maybe? Eh? Eh. All right.